All right, it's time to gear up for recap number 5. I'm going to suggest that you find your calculator and have that with you while we're working through this video. I have mine off to the side, so I'm not going to put it up on the screen this time, so you'll definitely want to be doing the numerical calculations on your own. Today we're going to talk about interpreting derivatives, kind of how to read them in a story problem, going over Riemann sums, and revisiting the fundamental theorem of calculus briefly. A note real quick about Riemann sums, and I'll mention it again later. There's a whole, I think 3 videos, all about Riemann sums back in the folder from the fall, because those were all done via video lessons. So if I'm going too fast or you feel like you need a bigger refresher than just this, might not be the worst idea to go watch those. Also, here I am over here apologizing because when I screenshotted stuff from AP Classroom, the font was really tiny, and I kind of forgot to go back and fix it in your packet before I posted everything. And quite frankly, I didn't take the time to go back and fix it, so I'm really sorry. Please accept my apologies. All right, interpreting derivatives. One thing I just want to go over real quick is that oftentimes you'll see in free response questions in the context of the problem, which means that you have to talk about the story itself. If the story is talking about bananas, you need to mention bananas. If the story is talking about water through a drain pipe, you need to talk about the water in the drain pipe. If the story is talking about a particle, you need to talk about the particle. Think about things in real life context, and the math actually will start to make more sense for you. So that's what I want to be careful of. You can't just say, like, the function is changing at this rate over this time. You need to say the temperature of the hot chocolate is changing at this, right? Like, be specific. Talk about the story, tell a story to the reader. So here's an example. A tire that is leaking air has initial air pressure of 30 pounds per square inch. The function t equals f of p. That's kind of weird. Models the amount of time in hours that it takes for the air pressure of the tire to reach P, representing the PSI. What are the units for F prime of P? So here, if we think about this, our input is PSI, and our output is time. That's weird, because we don't usually see time as an output, but that's what's happening here. So if I think about the F prime, that's representing the rate of change. So that's going to be delta y over delta x, right? Change in y over change in x. Well, our input is PSI and our output is time. So we are measuring time in all of this in hours, and PSI is just PSI. So we're going to be looking at D, okay? So setting up this little change in y, change in x, inputs, outputs, will help you keep track of your units, especially when we get to related rates. Okay, Riemann sums. Remember, a Riemann sum is a rectangular approximation for an integral. So if we don't have the ability to find the integral from, let's say, 0 to 3 of f of x dx, we can use rectangles to approximate. So I just have a blank coordinate grid here. I'm going to draw a couple different ideas. So here I'm going to have, we'll go with this. Cool. And I'm going to go, this is 1, 2, 3. So if I wanted to estimate the area underneath f of x, I could use rectangles. And the first method, the one we use often, is a right-hand rectangle. So I go to each of my partitions. If I was using 3 rectangles over the interval from 0 to 3, each one would have a width of 1. And then my heights would be dependent on the right-hand value of the function. Okay? So using a right-hand Riemann sum, I would figure out what is this height, what is this height, and what is this height, my right-hand heights, and I would add up the area of those 3 rectangles. And you can see that that's kind of like an okay approximation, because I'm missing all this area, but I've got this area and this area, so it probably checks out okay. The next one that I could do would be a left-hand rectangle. Again, I'm going to use partitions, partitions that have a width of 1. I'm going to use 3 of them, but this time my left hand creates my heights that are going over. Okay, so I'd find the area of this rectangle, and this rectangle. I also could do something called the midpoint. So I'm going to find my intervals, but then I'm going to use the height that's in the middle. Okay, so I'm going to find the height that's in the middle and the height that's in the middle, right? So I'm using the in-between parts of my partitions. And then the last one we have is not Riemann, it's technically a trapezoid rule. So it's where you're going to take the cut across between the two heights of the functions to get your approximation. Okay? So again, area of a trapezoid, we'll go over this again here in just a second. B1 plus B2 times H. But also remember, you can just take the right-hand rule plus the left-hand rule and divide it by 2 would be the same. Question is, when do you overestimate versus when do you underestimate? And so for 2 of them, it has to do with, is your function increasing or decreasing? The other 2, it has to do with, is your function concave up or concave down? So when your function is increasing, okay, so picture an increasing function, increasing, right hand is an over, and a left hand is an under. When your function is decreasing, the right hand is a little too low because your right hand values are getting smaller. Your left hand is too big. For concavity, if your function was concave up and you cut across a trapezoid, the trapezoid is going to be a little too big, while the midpoint is a little too low, because the middle that you would choose, this area that you're missing, is not going to be overcome by that area. So in our last one would be concave down. This time a trapezoid is going to be a little bit too small, and the midpoint is a little bit too big. And again, if you draw that for yourself, something that's concave down, the trapezoid cutting across is going to be too small, and the midpoint, right, this is too big as opposed to this little piece right here. All right, so right-hand example, let f be the function given by 9 to the x. If we want 4 subintervals of equal length, so we're going to have 4 subintervals, what is the value of the right Riemann sum approximation for the integral? So what I would suggest doing, we're going from 0 to 2. I like to just draw out a quick little number line, 0, 1, 2. And we're supposed to have 4 intervals, so we'll be at a half, 1, 1.5, and 2. And I'm supposed to use the right Riemann sums. So I need to find f of 2, f of 3 halves, f of 1, and f of 1/2. And then my widths are each going to be 1/2 wide. Well, to get the height of the function, I need to use f of x, which is 9 to the x. So my first right-hand rectangle, I'll draw this one, we'll say it's in blue, is going to have a width of 1/2 and a height of f of 2. My second rectangle is going to have a width of 1/2, right? So it's coming over this way, so a width of 1/2, and a height of 9 to the 3/2. This next one is going to have a width of 1/2, and this will be 9 to the 1st, which hopefully we all know is 9. Plus the last one, that was supposed to change colors. Last one will have a width of 1/2 and a height that's equal to 9 to the 1/2. So using your calculator, go ahead and pause, type that all in, see what you get for your right-hand Riemann approximation. Pause your video for right now. Okay, so I take it back. You could have done that without a calculator. These are our fractions that we get from each of the rectangles. They add up to 120 over 2, which means that this integral is approximately 60. All right, a left-hand example. See, this is where the font gets real tiny, so my bad. The function is continuous on the closed interval and has these values. Using these intervals, find the approximation of the left-hand Riemann sum going from 2 to 13. So this is where we want to box things off. I'm going to go, here's one rectangle using my left height. Here's my second rectangle using my left height. Here's my third one using my left height. And then I'm supposed to go from 8 until 13 using my left height. So the purple one has a width of 1 and a height of 6. The green one has a width of 2 and a height of -2. The blue one has a width of 3 and a height of -1. And the fourth one has a width of 5 and a height of 3. So we're looking at 6 minus 4 minus 3 plus 15. 6 minus 4 is 2. Minus 3 is -1. Plus 15 should be approximately 14. All right, this one we're going to use a midpoint rule. It says we have our function as continuous, use these intervals. So 0 to 2, 2 to 4, and 4 to 6. So we're going to have 3 rectangles to estimate 0 to 6 using a midpoint. So here, I want you to think about using the middle heights of each one. Pause your video and see if you can write out the answer for this. All right, so I got an answer of 8, right? Each one of those has a width of 2, 2, 2, 2, and then our different heights going through the midpoints. Notice that 1 is exactly the middle of 0 and 2. 3 is the middle of 2 and 4, etc. All right, a trapezoid approximation. On a certain day, here we have a rate, something with a recycling center. Use a trapezoidal sum with the 3 subintervals to approximate the number of tons in the first 9 hours since the center opened. So for our trapezoids, here's 1 trapezoid, here's 2 trapezoids, here's 3 trapezoids. And remember, we're going to do a right-hand sum plus a left-hand sum and divide by 2. So go ahead and try that for yourself, and let's see what we get. Again, sorry for the small font. Okay, so I got my right-hand rule in blue and my left-hand rule in yellow, and I came up with 68 tons. I want to talk super quick about units. So R of t was our height of our function, and that was measured in tons per hour. But then dt represents our change in time, so our change in hour. So notice that our hours cancel out, and we're left with tons, right? Because each rectangle would have had a height that's in tons per hour, and this would have been hours. So when you multiply them together, the hours cancel, and we're left with tons. Units are helpful in the context of the problem. All right, so remember to go from approximations to exact values. We get an infinite number of rectangles. Go ahead and look back over this and make sure you understand how those two things connect. Remember, A is your starting value plus the width of your step or your rectangle, how many steps you take, we're taking an infinite amount of them, etc. Ways to find exact areas under a curve would be to use geometry, the limit definition, which is this thing up here, or the antiderivative shortcut, right? The fundamental theorem. Approximate areas are Riemann's and trapezoids. Okay, so those are not exact. Those are only approximations, usually most often when you're given a table of data. All right, so the last thing, fundamental theorem of calculus. Remember, if you take the antiderivative of f prime dx, you end up with the original function. And if you take the derivative with respect to x of an integral from some number to another function, let's go h of x, and this will be f of t dt, then the cheapy little shortcut is you plug in f of h of x times h prime of x. Okay, so this one is antiderivative of a derivative. This one is the derivative of an antiderivative. Again, if you were a little bit confused or if that went too fast for our review, there's a whole video posted back in first semester if you've got questions to go over it. Or you could just watch my YouTube channel, because maybe I'm going to try to be YouTube famous in the middle of all of this. You just never know. All right, talk to you later. Go to your AP Classroom and let us know if you have questions.